Okay, so how many students are expecting today? So Ihtisham, you are ready?
Hello, sir. Can you hear me?
Yeah, I can hear you. Definitely.
Yes, sir. I am ready.
Mhm. Yeah, it seems you are ready on your picture also. You are ready.
Yes, sir. It was an old wedding of
Yeah,
some
it's a
of my close
party.
friend. Yes,
Mhm.
sir. Uh,
Okay, so Nargis, you are there?
Yes, sir, I'm here. Assalamualaikum, sir.
Walaikum salam. Okay, so I don't know if other people are coming or not. Usually they are late. I mean, okay, so today actually is 14th lecture. So most probably 15th is the last one. But it's not confirmed. Maybe some more things if I add. But most probably 15th will be the last one. So Tahura is here now. Tahura, can you hear me?
Yes, sir. Assalamu alaikum, sir.
Walaikum salam. So now I think it will be more convenient for you people because Zoom is better for even the internet is not very good.
Yes, sir.
Mhm. Mhm. So did you people go through my previous lectures?
Yes, sir. I covered the previous lecture.
All the lectures? All the 13?
Yes, sir.
Mhm. So did you have any confusion?
No, sir.
Mhm. So
I
you
get all
understand?
points.
Okay, so understand
Sir,
what is amplifier, what is oscillator?
yes, sir. Sir, the
Mm.
numerical in this lecture there is more numerical type,
Yeah, last
so
lecture. Yes,
a
last
little
lecture.
bit difficult for me.
Why?
Sir, because the 13th lecture was the more difficult, I think.
Mhm. Mhm. Yeah,
Um,
but you have a difficulty. Um, you can ask what difficulty do you have, and we may discuss uh, probably after this class or something like this. Whenever you feel convenient, we
yes,
can
sir.
discuss.
Yes, sir.
Okay.
I will ask in the group,
Mm. Mhm.
WhatsApp group.
Mhm. Okay, so thing is that I don't know, only three, four people are here. Uh, so how many will come? I don't know. So your sister is not coming, Tahura?
Uh, she is coming, sir.
Mhm. And Salman will not come definitely because he has a
Yes,
net
sir. I
problem always.
don't. Sir,
Okay,
maybe.
yeah. Okay, so in the 14th lecture, what we are discussing is mostly about its continuation. Uh, we have studied the oscillator, how the ultra short pulses are generated, more specifically femtosecond pulses, and then how it can be amplified, and the things which are important to manage. This is dispersion because the spectrum is broad. And so in this lecture, we are going to study, okay, we amplified something, but there are some issues. We cannot amplify directly. Okay, so amplifier, whatever kind of amplifier it is, it's multipass or whatever, there are some things which we need to consider. So that is why in this lecture we are going to study the CPA system. CPA, this is the chip pulse amplification. And why this thing is necessary this technique is very important whenever you study the ultrafast or femtosecond lasers, because when you have very short pulse, usually the peak power is very high. And if the peak power is very high, then the possibility or very high probability that if you amplify directly, it may damage the mirrors. Not only mirror, the crystals and some other optical elements. So that is why the technique which we called chirp pulse amplification. And through this technique, we amplify. Otherwise, they are troublesome always. So now we start. So we know already that in the oscillator or before actually, we discussed that the dispersion effect. So the dispersion effect basically, the lights, when they pass through any medium, transparent medium, so they move with a different velocity. And so usually what happens, the red is leading and the blue is lagging. So the same thing here you can see in this animation. This is your dispersion medium, and I'm just trying to illustrate the two prisms, okay? Otherwise, the configuration has to be, I mean, like a certain angle or something like this. This is just you people to understand. The light from here, if you see this white light means a broad spectrum. When it passed through this dispersion medium, so you can see it's dispersed. All the colors are dispersed. Red is at the leading edge and the blue is at the blue and purple or something like this. So when they enter here, the first prism somehow compensated, and in the second prism, it's completely compensated because when it passed through because these, if you see the prisms, these things, I mean, if you go back, you can so understand in detail. I think it discussed. When the light passed through from here, it covers, it means this is a thin portion here of the prism and this is a thick portion here. Okay. So this is more dense, this is less dense. And similarly here. So when the light passed through, the lagging one and the leading one, they are compensated when they pass through these prisms. Okay, so this is just to illustrate, just to show you that how the light is dispersed and then it's compensated. In actual configuration, if you remember, if you go back there, you can see the prism is adjusted at certain angles or something like this. But it's not only with the prism. We can also do it with the grating and some other optical elements, which I probably you may not have idea, so I don't want to discuss other optical elements. So here, the more important you people to keep remember is the prism or the gratings. Okay, so what next and why? What is the meaning of this? So we want to amplify. If we want to amplify, I told you that the light is very intense, peak power is too much because the pulse duration is very small. And so all the power actually is concentrated in a small, very small peak. Like if this is a peak here, so all the power concentrate here. Okay, let's suppose this is a 35 femtosecond or something like this. So amplify directly in this way. It's not convenient, and it's a bit risky, you can say. Like what is mentioned here, you can read the pulse intensity inside amplifier can become so high, okay, and highly probable that they may damage the optical elements, and it happens actually. I have observed by myself. So some possibilities are there to expand the beam. Okay, so if this is your oscillator here, then this is your amplifier here. So what you can do, you expand the beam using kind of telescope or whatever, lens or something like this. Okay, so use a large amplifier medium. So amplifier medium, the crystal. Okay, in our case, the titanium sapphire crystal. So use a larger size crystal in the amplifier. Okay, so if this is your crystal, that is a multipass amplifier. So this is crystal. So this crystal has to be, if you want to avoid, this is the simplest solution to make this size bigger and expand the seed which is coming from the oscillator or something like this, to expand the beam size, so a little bit bigger beam size. Okay, so if we want to amplify more, like you want to go to like millijoule, or you can say you want to go to terawatt, okay, not even gigawatt, more than that. So what we need to do in this case? So the easiest way that to expand the pulse in time after the oscillator, after the generation. So for this purpose, what we use a stretcher. You will see in the coming slides. So expand the pulse in time, in the time domain. Okay. So the time domain, when the pulse will be expanded in the time domain, so it means it will not be a femtosecond, but usually this expansion, it may go up to picosecond. Okay. And so if it goes to the picosecond, then it means it will be a very broad pulse. And so all the energy will be distributed in a broad pulse. It will not be very intensive in this case. So it's easier to amplify. And after that, another stages may come. Okay. So how we can reduce the intensity? By using the grating stretcher to stretch the pulse in time. So to stretch the pulse in time mean that the pulse become broad. So if the pulse become broad, then it will be less intense and you can safely amplify. After that, if we move to the next slide here, chirp pulse amplification, CPA. As I mentioned, due to the high intensity, intense field, intense light after the oscillator, it cannot be amplified directly. It can be, but it may not be feasible. It's not safe. It's not safe to amplify in this way. And so that is why this technique is used, which is called chirp pulse amplification. And you can see the points here, which is mentioned. To stretch the pulse in time, so peak power is reduced, and we can go up to hundreds of picoseconds. Okay, and then you amplify this stretch pulse. When you amplify this stretch pulse, it means that is not very intense, okay, but you can amplify it. And after amplification, to restore the original pulse, which was from the oscillator somehow, then you can compress it again. Again means to restore the pulse. So started from the femtosecond laser and you converted to you stretch to the picosecond laser, and then you amplify, one amplifier, two amplifier, depends. And after that, you compress it again. And so after the compression, you will get the same pulse what you have before the stretch. That is roundabout. I mean, there would be plus minus 10 femtosecond difference, but it will be in that range actually. And how it happens, you can see here. This is your original pulse from the oscillator. This is the generated pulse, okay? Then you stretch it in the time domain. This is all these spectrum in the time domain actually. So pulse is stretched in a time domain. Then you amplify it, this picosecond pulse, whatever it is. So you amplify, and after the amplify, when you amplify, you recompress or compress it again, or compress it simply. The gain word may not be suitable here because we haven't compressed it before. So compress it, and here if you see, this is a stretching. Sorry. Okay. So here, this is your pulse generation, this is your stretcher, this is your amplifier, and this pulse when entered the compression, and after the compression we get this pulse. It has almost the same pulse duration, femtosecond range, just very intense. Okay, and on the right side you see the graph, actually the plot, which just shows that how pulse, starting from this is starting, and then it is stretched here, and then you can see it amplifying, is intensity increasing, and then it's compression, and then go back. The same thing which you can see on the left side of this slide. Okay, so here, it's very interactive way. If you can see here how exactly this CPA process actually it happens. So pulse is generated, and it's a broad spectrum because it's a femtosecond. It's a broad spectrum. It has colors. Okay, whenever you show the broad spectrum, it means it has colors. Okay, and here is a generation. Here, if you see, here pulse is generated here, and here is stretch. You can see the colors are separated now because dispersion. And here is amplified. The same pulse duration is ran in the picosecond, and amplify here. So the amplified pulse is having a pulse duration of around picoseconds. Okay, and after this one goes to a compressor, and it's compressed back. Okay, it's compressed, and you have the same pulse duration what you have here. And if you have here 30 femtosecond, then most probably you will have here 37 femtosecond or something like this. Okay, so probably I assume that because of these animations, you people can understand in more interactive way, and or you can understand more how this CPA process happens, or how the CPA system works. So another view of this system, this is a picture, I figure I took it from one of the published article. So here, what you see here, these are electric field. This is electric field of the pulse. Okay, and this is your pulse generated before to enter in the rest of the system, which we call the chirp pulse amplification, CPA. So why it's called chirp pulse. Chirp pulse means that chirp is introduced here. You can see here. This is chirping. Chirping effect. Okay. Lights, the different colors, they move at a different speeds, with different speed. Okay. So that is, in simple word, we call it like it's a chirp is introduced in the system. So here, if you see, this is a grating. This one is, there will be only one grating actually, but this setup actually, this is stretcher here. This is like mentioned here. And if you move further, and this is your compressor here to compress, and you can see the chirp is removed. And this is your amplifier. So chirp, so in other words, in simple words, you people can understand in this way that the chirp is introduced, then amplify, and at the end, the chirp is removed. So when the chirp is introduced, the pulse is very broad, it's easier to amplify, and then after that, you can compress and restore your original pulse from the oscillator. Another animation you can see here, upper portion actually here, it shows the electric field. And here you can see the envelope, pulse envelope. Okay. So what is happening here, if you see, this is your original pulse, enter in the stretcher here, and it's stretched now, and it's amplified. Okay. And then it compressed. So this is a compressed one. Okay. So like here, I mean, if you, it's like this. And if you go here, then like this. And if you go here, then like this. And at the end, something like this. And this one, like this is the envelope actually. So you can see the red one is the leading one, and the blue one is the lagging, the most at the end, at the tail actually. And this dotted or dashed line, it shows the envelope. Okay, so overall spectrum will be like this. Envelope actually. Overall, that would be like this dash you can see here. So if this is stretched here, this is envelope, you can see this one. And now, and after that, envelope actually. Overall, that would be like this dash you can see here. Hello. So I can hear my voice somewhere. Okay. So this is how I mean it, probably you people can understand. Okay, now setup. What kind of setup it will be? We know that there will be a grating stretcher, amplifier, and compressor. By sure, these components are these are essential parts of the CPA. So here you can see here, this is your femtosecond pulse here, and this is the configuration of the stretcher. Okay, we'll see in the next slide probably. There are some specific configurations of the stretcher which is used. One grating and some other reflecting type mirrors. And after that, this is, you can see, is the amplifier, multi-pass amplifier. If you go back to my previous lecture, you can see this one. And this one is compressor, using two gratings. Okay, we will see in the next slide. The same thing here, but this configuration of the stretcher is different because they are using two gratings here. Okay, so it's a bit tricky to understand, but you may have some I mean, like a blend of some idea to understand what it could be actually. This is your pulse generated from the oscillator, then it enter here in the stretcher, and it makes some passes, and then it go back. And from here, it move to the amplifier, and from amplifier here, it goes to the compressor, makes some 2 rounds, I think, and then it goes back, and you get the pulse at the output. Okay, so if you think like on the optical table, it's not so simple to build this one. Maybe when we teach or when you show the diagrams. So in this case, probably it's not. It may be, but may not be. Seems very difficult. But in actual, if you make it on the optical table, it's not really easy thing to do. Okay, so one more actually, if you can see this, this is also animation. You people to understand more, you can see here. I show in the form of blocks. So this is an envelope actually, and oscillator. And starting from the oscillator here, and then you go to a stretcher, stretch completely, and then it's amplified, the same stretch pulse. Then it's compressed back. So here you have, this is exactly the same pulse what you have at the beginning here. Only is very intense, amplified. This is similar kind of thing, but down you can see I show the different colors here, and up is electric field. How electric field? I mean, you can illustrate in this way. So with the oscillator, when there is no chirp, okay. So here, if you see, there is here no chirp. Now, when you enter in the stretch, chirp is introduced, and this same with the chirp is amplified, and then at the compressor, remove the chirp. We got the intense field beam at the output. Okay. So here the chirp introduced, so colors are separated here, and in the same way it is amplifier here, and it's compressed so that the chirp is eliminated somehow. Sometime it stays there. We have to tune to adjust the grating stretcher and the compressor. So this one is a stretcher configuration. Okay. What is here? This is your grating. So what exactly grating? I assume that you people know already. It's a ruling on the, you can say on the kind of mirror. Yeah. And these rulings are so many rulings, like here 1400 per millimeter. So it disperses the light when the light falls on it. And here, if you see, this one is a convex mirror. And here you have a concave mirror. And if you see the configuration, probably you can understand this is the input beam from the oscillator. It goes to the grating, it disperses, colors are separated, okay? But if you see that this grating is adjusted at certain angle, it's not straight, okay? So if it is not straight, so it means there is a purpose. So you can see the which light travel less, which light travel more. Okay, you can easily guess from there. And here, if you see that this is a total envelope, what exactly happened in the stretcher, that pulse is stretched. This one is showing the pulse is stretched. This is the original pulse. Okay, and then it's stretched slowly, slowly. So here it stretched. Okay, so stretch in the range of picosecond or something like this. So you can also read this one. I mean, it's maybe you can understand that pulse stretcher utilize the same principle as a compressor, but opposite. Okay, so we'll see the compressor as well. It separates the spectral components because of the grating, and so that it can be, the delay can be manipulated. This is your compressor. In case of compressor, this configuration showing there are, I mean, two gratings are used here. Okay, so you have, this is your input beam here. Okay, it shined on this one, and then it dispersed and shined on here. So disperse, it means that different colors are there, and because here if you see that the grating angle is also, it's not a straight, it's tilted to a certain angle. Okay, so it means that both the lights will travel with a different different distance. Okay, so it's compensate which one is going faster, which is slower. And here you can see here it's opposite to the stretcher, and the pulse is compressed back here. It's showing the compression. So chirp is removed and it's compressed. It's starting from like here, it's stretched and amplified, and it is compressed now slowly in the compressor. So here is compressed. Okay, so we can control or we can optimize the whole CPS system to change or to optimize the gratings. Mostly, it depends. I mean, it can be optimized to tune or to change that little bit the angle of the grating in the stretcher or in the compressor. So, what is the meaning of changing? This is your compressor. Okay, we can change the separation between these two gratings, and this separation is very critical. So, with changing the separation, we can fine tune the system and to have the minimum possible pulse. And we can also change the angle, and both has to be parallel to each other, both the gratings. Okay, so changing the distance, this is a more conventional kind of thing to optimize, to tune the system. So this plot is showing here grating detuning. Grating detuning means there are separation between the grating. They're changing the separation between the grating. These are gratings, okay? So this separation is changed or tuned in steps, okay? So 200 millimeter, 400 millimeter, and minus 200. Minus means if you set one point here, move on this direction is positive, and move on this direction is negative. Okay, so if your grating is like this, and this is a separation, and you are moving one grating, let's suppose this grating, and if this grating move in this direction, if this grating move in this direction, then okay, anyway, in this direction is positive and this direction is negative. So, and what is on y-axis? This is a pulse duration. So you can see here, when we change the grating separation, this curve, you can see here, and here around this area, we have minimum possible pulse. Okay, so with the help of this compressor, we can tune the CPS system. And you can see here, this is the minimum possible pulse duration. So if we set it here, you can see it will be like 70 or something like this. And if you set it here, it's 100. So it means there's still chirp is introduced, but minimum possible pulse duration means that the chirp is removed completely, or at least the minimum we have. Okay. Stretcher and compressor, actually, they are very important in the CPS system. And they are exactly opposite of each other. Okay. So you introduce the chirp, or you stretch the beam in a picosecond, and with the help of stretcher, and then in the compressor, you have to do opposite of it to compress it back. And this graph on the right side, actually, what it shows that material dispersion, the refractive index of any material, it depends on the wavelength. And if you go back the last lecture, I showed you one equation, which is Selmier equation. And it shows clearly the relation between the refractive index and the wavelength. Okay. And so this plot, actually, what it shows, it's very clear here that the wavelength and the refractive index. So if you have a lower wavelength side, then refractive index is high. If you go to the higher wavelength, then the refractive index is lower. Okay. So higher wavelength side, the refractive index is lower. Okay. So to understand this, maybe probably you can go back to the previous lectures. Hopefully you can understand more. Now, I don't know this term, you people, but at least you people can try, actually. Spectral amplitude and phase. If we have this spectrum, this is spectrum, and it has a peak. Okay. So the amplitude is on the x-axis. Okay. And here, what we see is frequency and phase. What is this phase? Phase, what exactly this phase is?
State of motion.
Who said?
Salman.
Phase of motion. What do you mean, phase of motion?
State of motion of the wave. Phase
Of
of
what?
motion, nahi.
Hmm.
State of motion
State of motion.
of the wave. Yes, sir.
Okay, probably you, but in more simple word, you'll see here.
I
First,
think that this is related with the intensity, because
yes,
the phase is related how the wave is up
yeah,
up down or down one or down.
yes, yeah.
Okay.
Actually, it's like this. Okay, so
Yes.
it can be here, it can be here, it can be here. Okay, so that is why this is the frequency here, and that is the phase, and you have a straight line here. Probably you can understand from this statement here. At what point in the wave cycle is the wave starting at crest or trough? So that is the spectral phase. Okay. Amplitude is very easy to
sir,
understand. Yeah.
and that is how we define the phase for a specific wave.
Yes.
That at what point it start.
Yes.
Either it start at the crest, trough,
Yes.
or anywhere between them,
Yes.
they define the motion,
Yes, it's
the
true.
motion of light wave.
Yeah. Yes, Salman, you are right. Actually, you are. I was not expecting you that to be here. And
Sir, actually, we have a dinner party here, so that's why I late. And I forgot the class though, but
uh-huh.
Urus remind me
Okay. So you have a party in
the class.
your hometown?
No, sir, at college,
At
at the
college.
institute.
Hmm.
Yes.
Yeah, I mean, you have a least interest to take this course, but anyway,
No, 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 sir. I do not have least interest, but due to that program, I joined late, and actually, I forget about the class that
what kind
today's
of date it
also the
is?
class.
What kind of date it is?
Uh, Today, 23.
No, I'm saying other kind of date. Anyway, uh,
Okay.
okay.
Very near. Soon, sir.
Yeah,
Inshallah.
yeah, that is already. That is why you are in the picture. You look like you are already married.
In the picture?
Yes, in the photo. I mean, what you have in the suit.
Oh, okay, sir.
Yeah. Okay, so let's move here, and to understand the phase and the spectral phase, probably you people can guess from here, or you people can Google somehow to understand more. Actually, this is necessary to know. One more thing, actually, it may help you to understand what is this spectral phase or what is this kind of thing. First thing is that phase is a function of frequency. Okay. Phase is a function of frequency. Here you can see in this plot. This is the phase value here, and this is the frequency. Okay. So it's how it changed the frequency and the phase with each other. In the upper portion here, it's you can see the blue one is amplitude. It shows the amplitude, and the orange one, it also shows the amplitude, but blue one is higher amplitude and larger amplitude, and the orange one is lower amplitude. Okay. So phase is the same here. This one and this one. Okay. They are passing through at the same point. Okay. Crust to crust, trough to trough. Okay. In other case, what you hear, the amplitude is same, but the phase is different. Okay. This one is almost like one is passing from the crust, one is passing from near the crust, one is passing from the trough, and one is nearby. So not exactly, in this case is exactly like this, but here it's not exactly like this. It is like this, and other one is like this. Okay. So the phase is not same. Amplitude is same. Okay. Amplitude is same, but the phase is not same here. Okay. Keep remember this thing. Now, we know that what is CPA system. Okay. And I hope Salman also knows now. And what is the grating stretcher? What is a grating compressor? So we know these parts of the CPA, the components of the CPA system, but we need to know some things for some things being related to dispersion. And for this one, we need to understand some equations. And these equations link with the both stretcher and compressor. This is Taylor's expansion here. If you see here, this one, this is Taylor's expansion. All the people, I think, all of you have studied this kind of equation in the physics. Okay, so different terms are here in this Taylor expansion. Okay. For us, actually, the important term is this one, second order term, the second order term, and why this one is important, you can easily understand from here. But the first one is showing it's just a phase, is a constant phase here. And the second one is showing the group delay. And the third one is showing group delay dispersion. If you go back to the lecture, you can understand. I mentioned this one in the previous lectures. So GDD, group delay dispersion. First, you need to know what is GVD and then GDD. And then you have third order dispersion. There are different kind of dispersions there. Okay. When the light spectrum is very broad and it passes through the dispersive elements, optical elements, glass or whatever it is, then it means there are different kind of dispersions. And these dispersion, the most prominent one is GDD, second order. Third order also exists, but third order sometime we neglect. Okay, so GDD is very important term. What this plot is showing, probably if you can understand, this is simple phase, constant phase here. Okay, and here phase is changing, the linear term, linear, the phase is changing. But the important thing is this one, this corresponds to this equation, this first term. Okay, and then you have actually this one first and second, this one and this one. Okay, so if you see here, this one and this one, here is a constant phase, here phase is linearly changing. Okay, and then you go to this quadratic term, which is the group delay dispersion, GDD, second order one. And the change usually is like this. Okay, so frequency versus phase, frequency versus phase. Then you go to the higher orders, that is cubic term, third order dispersion. Then you have like here, this is the frequency and your phase term. In this case, it will be changing like this. And if you combine all these, it will be like this. Most important thing, this one and this one. This one even less, but this one is very important because this kind of phase, group delay dispersion, you often observe in the femtosecond laser system. So you have to diagnose it and you have to try to eliminate it or whatever it is, this dispersion. And this dispersion, the phase is behaving like this. Okay, with the frequency. Okay. So what is this red one actually is showing that we can ignore all these terms for time being, and we only consider this one because this is the important thing at the moment. So if we consider this term, okay, the dominant term, and this is the second order dispersion, GDD. What this plot is showing, if you go back to the slide here, this is the shape, the trend. And the same trend you can see here. This is a phase here. This is a frequency. Okay, omega, definitely is angular frequency. And what this orange one and what this blue one is showing, that this one is greater than 0, the positive GDD, and this one is negative GDD because phase is less than 0. Okay, but the trend is same. So what this trend are showing, you amplify something, you compress something, and at the end actually you see the pulse. But if you make some measurements, still you can see this kind of if you measure the phase and the frequency. Frequency is what? I mean, from the wavelength you can convert to the frequency. So you can see this pattern. Okay, so it means if there are this kind of pattern, it means there is group lay dispersion, kind of dispersion is there. If you get like straight line, then the phase, there's no change in a phase is constant. That is ideal case. Okay, so if you have GDD, group lay dispersion, then you have these plots like this, the trend. So in this equation, why I'm showing the plots, because with the help of plots, probably you people understand more somehow. This equation, it has terms which you already probably know. This is your angular frequency, and this is the central one, and this is the phase term, second derivative. Okay, the phase term of second derivative. Now, the key equations, we are studying the key equations starting from this one. Okay, so GDD. First thing is that we know already that we are using in the system grating pairs or prism pair or other things which I did not teach you intentionally. That is fiber Bragg grating. That is probably beyond of this level at the moment. But two things, we use the grating pair and the prism pair. Okay, and why we use this one? To compensate the dispersion. Okay, and when we compensate the dispersion, it means we need to tune it. We need to move the angles of these gratings or the prisms to optimize. Okay. Now, this is the standard equation for GDD. Okay, second derivative. And this is what it written here. The amount of time stretching introduced by the stretcher. Okay, so how much stretching is done? Okay, and we can use this equation to find out something related to the stretcher. In a more simple way, we'll see later. But this is a standard equation here. So if you see in the plot here, it's a similar kind of thing, like you have seen in the previous slide. This is your angular frequency. And this is your spectral phase. So this is your angular frequency. And with the angular frequency, your phase is changing. When the phase is changing, so GDD is also changing. So GDD from 0 to 2 or something roughly. So when this is kind of curvature of the spectral phase. Okay. So if this curvature is bent more, as you can see, then it means that the GDD is very high here. If it is flatter a bit, then GDD is lower. Both these graphs are showing like this. The lower one showing the GDD value and the upper one showing the spectral phase, the GDD, the phase, how the second order phase is changing with the angular frequency. And it means that if this one, the curvature is higher, then it means that the GDD is higher. If it is straighter, then the GDD value is lower. Okay. So this equation is important to understand. Now, if you remember, I mentioned that the compressor and stretcher, they are opposite of each other. Stretcher stretch the pulse and the compressor compress it back. So the factor of compression and stretcher is supposed to be same. Okay. And like one is introduce the dispersion and other one is you can say that remove the dispersion. Okay. So here, if you see, this is your compressor and this is your stretcher. So stretcher actually, it introduce the chirp. That means dispersion. Okay. And exactly opposite compressor actually. It remove the chirp and compensate the dispersion. So they are exactly opposite. Only negative sign shows that they are opposite of each other, equal and opposite. Okay. So it means that GDD and GDD of the stretcher and the compressor is supposed to be same, only in the opposite direction. Okay. Here you can see very easily, like this is the stretcher, this is your compressor, and this is stretcher plus compressor. Here, GDD introduced, and it's positive GDD here, and here is a negative GDD here, because it's a negative side. Here, the scale is phase. Okay. So obvious that from the phase you can calculate the GDD. But here they are showing specifically the phase, positive and negative. And they nullify each other. And at the output, you get this one. This equation is also very important. And what it shows that the stretching, how much the pulse is stretched. So with the help of this equation, you can physically calculate. Okay, so it's definitely it's a temporal, the stretching mean is a temporal broadening here. And how much it is stretched. And GDD, how much was the value of GDD? It is the frequency here. Okay. And this one is your initial pulse before to introduce in the stretcher. So before to introduce in the stretcher, it's like 30 femtosecond or whatever it is. And you have these terms now, and this term also, the spectral width of the pulse. And you put these values, and then you can calculate how much stretching is happened or how much stretching do you want. Okay. And the plot, if you see down here, that plot, what they're showing that on the left side is the GDD and the right side is time. Okay. So here, stretched pulse and GDD. So here you have, this is the minimum value okay, when the GDD is 0. When there is no GDD, so it means there is no stretching. So what is the purpose of the stretcher? To introduce the dispersion. So if the GDD is 0 here, it means there is no dispersion. And so the stretching, 0 stretching here, okay, almost what you have from the oscillator, okay. And on this side, if you see, this one is intensity definitely and the time, and this is your pulse duration, okay. And what happened with the introduction of the dispersion, this pulse duration become broader, okay. It started from here, and with the introduction of the GDD, when the GDD is increasing, this pulse width is also increasing. Okay. So when it goes down here, you can see this is a minimum pulse duration. And then when it start up, then you can see the expanding. So this is how, I mean, with the help of a stretcher and the compressor, same thing you can apply to the compressor as well. Stretcher basically is to stretch. This kind of plot actually is more suitable for the compressor. If you remember, I have shown before as well. So this is your CPA system physically existing in the lab. Okay. To understand in this way, I don't know how much you people can, but there are few terms are used here. The pulse duration of this system is 20 femtosecond, and the peak power 3 terawatt. It's huge peak power. 3 terawatt, the peak power, not the average power, okay? So peak power means the peak goes up. Okay, so power, this one is this power. And 10 hertz. So 10 hertz, basically, it's a repetition rate. I discussed this thing a little in my previous lectures. So 10 hertz, like you convert into the time, 1 over t. So after this much time, the pulse appear. Okay, so this is called the repetition rate. So repeating. Okay. Now, if you see this diagram in the center, this is your oscillator, if you remember. Okay. And these are pump lasers. This is oscillator configuration. Here, the crystal is here, and you use the prisms. Okay. And after that, using different method or to guide the beam to the stretcher. Okay. And from the stretcher, you go here. This is 8-pass amplifier. Okay. And from here, there is another amplifier, which is 5-pass amplifier to boost the peak power more. And then you go out. And this frog and spider, this is probably difficult for you people to understand. After the amplifier, you go to the compressor here. And after the compressor, you can use this beam for different applications, whatever, for different kind of applications. And here, if you see, this is different portions. This is your oscillator. Okay, this one is oscillator. You may not see probably, this is a crystal here. And these are the cavity mirrors. Okay, and the prism will be somewhere here. Here, this one. And other one is somewhere here. Okay, So this one is, and the green light is a pump light, a pump laser. Okay, so this is your prism, and this one is your amplifier here. If you remember, we studied the amplifier. Okay, this is the crystal here, and you can see the beam passes through this crystal many times. And this green one is pump. Okay, and this one is the other amplifier, which is called the power amplifier. It boosts the peak power overall. And this is how the overall system look like. Okay, this is one kind of CPA system. It has two amplifier, it has oscillator, conventional oscillator, stretcher, and compressor, and two amplifiers. And the repetition rate is 10 hertz. So after, if you convert into the time, 10 hertz. So, so after that much time, the pulse appears. So 1 over 10, 1 over 10 is equal to what? Like you have frequency here, T. So T is equal to 1 over F. So it's 1 over 10. So it's what do you mean?
0.1.
Yes. So this is the repetition rate. After 0.1 second, the pulse appear. Okay. So second CPA system, you can see this is also a terawatt system. Okay. And it's 1 kilohertz. So 1 kilohertz, when we see this the laser beam, we don't see it's blinking, or it's like our eyes cannot detect. So F is equal to 1 over T, and you can, T is equal to 1 over F. So it's 1 kilohertz. So how much it will be? 0.001 second. Okay. So we see as a continuous beam in this case. So this is the oscillator of this CPA system. Here you have a stretcher. Okay. And here you have a first amplifier, which is the ring type, and the second amplifier, which is a 4-pass amplifier. Okay. And then you have this compressor. Okay. So this is another CPA system, and that CPA system have a different repetition rate, and pulse duration is somehow same, but different repetition rate. And this is whole system you can see on the optical table. And here you can see this portion with the amplifier. Here you can see this portion with the oscillator or something like this. This is the output spectrum of the system. Wavelength, intensity. So this is a spectrum, and this one is also spectrum. This one for the 33 femtosecond, 5 millijoule energy at 1 kilohertz. And this one is 20 femtosecond, 60 millijoule energy at 10 hertz. So output spectrum, if you measure the laser, then it looks like this. It depends. Okay. Now, at the end, actually, with some examples, let's assume actually you want to make a CPA system. And what thing you need to consider? There are so many things actually you need to consider, but a few things I'm mentioning here. Here, if you see, the gain, stretching, chirp, and group velocity dispersion for the titanium sapphire crystal. There are so many things actually, but the important some of the things I choose and so that you people can have a little idea about it. First, if we try to calculate the stretching, the chirp calculation, initial pulse, we know that what is generated 30 femtosecond, okay? And stretched pulse, we say 1 picosecond. We want to stretch up to 1 picosecond. And center wavelength, the spectrum, it has 800 nanometers. And the width of the spectrum, full width of maximum, that is 20 nanometer. Okay. First, we need to calculate the bandwidth in hertz. So which bandwidth? That delta lambda, which is given, this is 20 nanometer. Okay, so first we need to convert into the hertz, which is this formula. Okay, so C is here, lambda is center wavelength, and this one is, you substitute the values, you get this one. Okay, about 10 hertz, 10 into 10 to 12 hertz actually. So first thing we did to convert into the frequency. Second thing, to find out the GDD. And for this one, these are the equations. I'm not supposed to derive actually. Okay, these equations are existing already in the literature. Okay, and you need to understand these equations. You can also find from the literature for some papers or something like this, or from some books as well. Here, your pulse duration, your initial, your what will be, how much will be stretched, and this beta, and what is this beta? Beta is equal to this formula, okay? You have to find out the beta, and this beta is a kind of depending on the pulse, that how much it's stretched or you want to stretch, okay? And we know these values. You substitute and find out the beta, and then you substitute the beta here, okay? And you can calculate the GDD. By the way, this formula is showing how to calculate the beta value, okay? So this thing is separate. Okay, approximate GDD is the other formula. And here, how you can calculate the beta, because for the GDD to calculate, we need the value of beta. And for the beta, this is the formula. So we rearrange and we substitute these values and we calculated this beta value. Okay, so this is the formula which you can also use to calculate the GDD. D here is the GDD. Okay. And from where this formula comes, that is coming from the literature actually. It's not necessary to drive here, as I mentioned before. You just need to know these formulas and then you can apply. How to apply actually. So we have beta value, we have frequency, we can calculate this GDD. Okay, so that is around 566 femtosecond square. Okay, so if we plot the frequency on this side and the beta value on this side, so we can calculate the D value at any point. D is GDD. So here we have around 10. We calculated the 10, the frequency, and beta is around here. So here, this is the point actually. So this one is the D value, which is 566 femtosecond square. In the second example, here what we calculated, actually, we calculated the GDD. And when the stretching factor is given, stretching time is given, and we calculated the GDD, how much GDD is introduced. In the other example, we are supposed to use the other formula, which is simpler one, to find out the gain. Medium we use here is titanium sapphire, and the input energy actually 1 nanojoule, desired output energy is 1 millijoule. Okay, so gain we can calculate with this formula, which is 10 to 6. Okay, and if we calculated the gain, we can also calculate the number of passes in the amplifier, in the second or first, whatever amplifier is. If this is your crystal and you have this amplifier configuration, okay? So if this is the amplifier configuration, so how many passes, how many time it passed through the crystal to produce this much energy or something like this. Okay, so small signal gain. If you go back when we studied in the amplifier, actually, we discussed this thing actually a little bit. The small signal gain per pass, that is 2. Okay, it's a typical value. I mean, it's kind of a roundabout idea. And other gain we just calculated, which is this one. Okay, so this is basically G. And that one is G naught. Okay, so we use this equation. And from this equation, we can calculate this N. And that N actually, these are the number of passes, which is showing that 19.93. So 20 passes. Okay, so 20 passes. If we know the gain, if we calculate the gain, and we assume that the small signal gain, which is usually around this value, then we can calculate that how many passes in the amplifier we need. Okay, so what this plot actually showing, this is number of passes and total gain. Okay, and so it's a straight line, kind of exponential, not exponential actually, it's a straight line. So it's a proportional kind of relation, and you can find out the value of N at any point. It depends, like here, 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 and here. What will be the gain here? If you have this much passes, what will be the gain there if you have that much passes? But the important thing is that the formula, that gain formula, and then this other formula with the help, you can find out the number of passes. There are other methods also, but I'm showing these in a much more simple way, actually. So we need 20 passes here, okay, so that to achieve the desired gain, okay, that is 10 to 6 or something like this, the previous one. Okay. Now the third one, to calculate the GVD of the titanium sapphire crystal. Titanium sapphire crystal itself actually is a kind of semi-transparent actually. It's a transparent actually, red color. And it has its own dispersion as well when the laser passes through. Center wavelength we know. And it has certain properties, which is which you can find in a data book of titanium sapphire material. And So specific length, okay? For 800, at 800 nanometer, the GVD value for this titanium sapphire material properties is around 70 femtoseconds square per millimeter, okay? And we are supposed to find out GVD. So we need to consider the length. So how long this gain medium is, this titanium sapphire crystal is, okay? And here it is assumed that it's 5 millimeter. So total GVD and what is the material GVD, which is 70, and how much length? 5 millimeter. Okay. So the total GVD of 5 millimeter long titanium crystal is 350 femtosecond square. So whenever we design the system, we have to consider this thing as well. And this much the GVD is also needed to compensate. And compensation, how it is done? Well, we use the prisms or gratings. Okay, so tune them and put them at proper angles or something like this. And the plot here, what it shows that this is the crystal length here, and this is your total GVD. Okay, so it's kind of a linear relation. I mean, if you increase the crystal length, then the GVD is increasing. Obvious with the length, the GVD is increasing. Okay, so at the end, what these examples are telling you, you know that when we started the ultrafast stuff from mode locking or something, I mentioned you many times that the dispersion management is very important here because of the broad spectrum. Okay, so to understand this thing and calculate properly how much stretching is needed, and so that we can reverse with the compressor or something like this is necessary to calculate, and with the help of these equations we can calculate. And these are crucial steps. Compressor and the stretcher and the compressor, they are very crucial in the CPA system. And other thing, the GVD value in the crystal. And if you have any other transparent material in the system. So it's necessary to know how long crystal is used. So that is needed to be compensated. And so that is why these kind of examples are necessary to show you people and people to have some ideas. So that's all for today. Lecture number 14. And this lecture okay, so this one, what I said that these things are almost, this course is going towards the end of destiny, and probably next one is the last lecture, most probably. But I will see if some things are needed to add more or something like this. So if you have any question from today's lecture, I don't know how much you people understand, but at least 10, 20, 30%, most probably. So if you have any question, you can ask. Or if you want to ask later, it's also up to you. How many students are there today?
Hello, sir. I have a question, please.
Mhm.
Sir, we calculate the GDD for calculating the shaped length of the pulse. But why we have calculated the GVD? What's the use of GVD here?
Have you been to my previous lectures?
Yes, sir, I
Group,
was present.
whenever there is dispersion,
Yes, sir.
so group velocity dispersion.
So,
there is, yeah.
Actually, the purpose of my question was that we have calculated the group dispersion, delay dispersion, because we needed in the formula of measuring the shaped time length of the pulse, which we have calculated before in this today lecture. But I am confused about GVD, how it will
The
be
crystal.
useful for
GVD for the crystal actually. Okay, this is it's not supposed to be at the end. Okay, I mention at the end, but GVD actually it comes in the beginning when you choose the crystal, when you buy the crystal.
Okay.
So at that time you calculate, but when you make overall system, maybe this GVD is negligible. Okay, but in some cases it has to be considered. And especially with the links with the length of the crystal. That is why I say GVD. I didn't say GDD, GVD. Okay?
Sir, and
Yeah.
another question that we use the compensator for dispersion in the laser medium, but when we have introduced the amplifier into it, so we actually this dispersion was desirable in that, so that compensator was not needed anymore in this case now.
Which compensator is not needed?
Sir, first, when we have studied about the dispersion, that this dispersion is non-desirable in this laser medium because it actually separates the colors and
Okay.
it results in the chirping effect. But when we have gone towards the CPA system, in that we have stretched the pulse, and in that we actually
But
did the chirping.
yes, so I actually explained this
So-
thing. Why do we need this thing?
So I know why this is needed in here, but now the compensator is not needed anymore because we require dispersion for amplification ahead.
Why do we need the dispersion at the end? Dispersion, it has to be eliminated. So we introduce intentionally to broaden the spectrum. So because we
Yes, sir.
wanted to amplify, if we don't do it, we cannot amplify properly because it will damage everything. This
Yes,
is
sir.
the purpose.
But yes, sir.
Yes.
But before amplifier, we actually used the compensator because there was also dispersion in the laser active medium where laser was amplified in the cavity. So where we used two prisms for the.
That was oscillator. That was Iksham, that was oscillator. In the oscillator, you have to have a separate setup for the dispersion management. And the CPS system comes after the oscillator. And the CPS
Yes, sir.
system has its own.
So,
Yes.
sir, when actually in the amplifier system, we needed that dispersion. So we shouldn't compensate in the first case in laser oscillator if we need the dispersion after all in the amplifier
No,
region.
actually, no. In this case, we don't know actually how much is needed to be compressed. So the thing is that oscillator is independent system. Okay. So independent system means it can be used independently as well. Okay. So how much we have at the output of the oscillator, this is our this is our kind of final point that we need to have that much femtosecond at the end of the amplification. Like if we have at the end, like oscillator gives 30 femtosecond. Okay. So in this case, we need to know that after the amplification and RPS-CPS system that we should have around 30 femtoseconds. If you mean that we should not compensate there, then if we cannot compensate there, first thing is that we cannot achieve the mode locking. And if we cannot achieve the mode locking, there is no laser. If you go
Okay, for
back to
mode
my
locking, it
lectures,
is
I
also,
mentioned this
yes.
thing. For the mode locking, you have to control this dispersion in the oscillator.
Actually, sir, first we have studied about the mode locking, and then we have studied about this dispersion. So I was confused that it was needed in mode locking too.
Okay, maybe the sequence is, but if we have so much dispersion, we cannot mode lock, because mode locking condition, you know that. If
Yes,
you
sir.
go back and
Thank
if you
you.
see, yeah.
Thank you.
Okay. Okay, I mean, it's good that you have a question, whatever. I mean, it's good that I really appreciate. Who else?
In this case, we only see the electric field and the magnetic field have a similar behavior.
No, actually, you cannot. I mean, electric field. I mean, I mentioned to show that, but actually, the light has both the things. It's electromagnetic.
Yes, but usually they put only one field because you can
to show
derive
that.
the other.
Yeah, you show in this way actually, but the light always have two fields.
Okay, thank you.
Okay. So, I mean, Nargas, did you understand?
Yes, sir, I understand. Sir, I have a question. There was in our diagram, you used the beam splitter. Why we were using the beam splitter?
To split the beam.
Okay, but why do we need it?
Why do we need to split the beam? That's what I'm saying. I will send you some papers and then you can understand this is because at the moment you cannot understand the system, how it works. Okay. This is just theoretically I'm telling you the things here. But when you put the things on the optical table, that is a different story somehow. But the main principles are same. Okay. So the beam splitter is a very small thing. Okay. So, but how to use this beam splitter, that is the important thing. But I cannot tell you here in this way that, but show the proper diagram and how it works and how it goes. And then why do we need this beam splitter here and etc. This is like this.
Okay, sir. Sir, my major question was that why we're using it here? Why do we need to, in this configuration, we need to split the beam? That was, I was thinking.
When you do the work with the like optics on the optical table, there are many places you need to use a beam splitter to split the beam. Half of the beam is going to the amplifier, maybe half of the beam is going to the other part of the system.
Okay, sir.
Okay. Okay, so Ali, did you understand anything?
Yes, sir. Except some mathematical formulas,
Yeah,
almost
I mean,
everything.
Pakistani students are they are stuck with the mathematics always. But you don't need to drive all the time. Sometimes you need to
Yes,
use it. So derivation comes, yeah, I know that in the system that most of the students, they concentrate on the driving the formula. So when they don't understand the formula, so they always think to drive the formula.
sir.
But yeah.
Yeah, you're right. Sometimes formulas are difficult to remember, but their derivation is easy.
Yeah, I mean, this is experimental kind of thing. So in experimental kind of thing, you cannot drive all the time the formula. So you keep remember, if you practice, these are very small formulas. But if you
Yes,
need, you can just, there are some articles who has not the 100% derivations, but they have explained these formulas.
yes, sir.
Yeah, so it's not coming from nowhere. It comes from somewhere.
Yes, sir.
Okay.
Yes, sir.
So, Marashu.
Yes. Uh, well, it's about the use of the Taylor expansion.
Mm-hmm.
And if o sea, the Taylor expansion has to we have to use it, but in some conditions.
Yeah.
So it have to it depends of the bandwidth of the bus, or
Yeah.
maybe another extra condition.
Yes. Yeah. But have you seen the CPA system, Mauricio?
No. It is, well, the component, the setup of the system, it's really interesting.
Okay. So, David, I mean, probably there are what you were calling that the institute there in Mexico. They have these CPA systems probably.
CEO at this Investigation Center in Optics in
Okay.
León, Guanajuato.
Okay. Yeah, I mean, I asked you to send me the website, but you didn't send me. So they must have this kind of systems, I think. Okay, so Salman, are you there, Salman, or are you tricking here? Okay, so who else is here? Tahura Hadi and I think they left. Okay, so we conclude here, and hopefully the next one is the last lecture, and probably I may send some assignment or something like this. I will see. And okay, so thank you very much for attending, and hope to see you in the next class. Okay, thank you very much. Bye bye.
Bye, sir.
Allah Hafiz.
Allah Hafiz.